Okay. Okay, so last semester we were dealing with the idea of finding derivatives, and of course we know that the derivative was the instantaneous rate of change, also known as the slope. So as we go through all of this, the interpretation last semester, derivatives was all about slope. But as we transition into the second semester, when we take an antiderivative, which is actually going to be known as an integral, we use those terms kind of interchangeably. The physical representation of the antiderivative is actually just a very simple idea, which is the area between the curve and the x-axis. So we're going to look at a couple of pieces through a very, very simple lens, and then I'll take you through let me see if I can find the share. There it is. To what happens when it's not so simple. So let's just start here. I had a couple of questions that are laid out. So for example, I have this very first question. This is the symbol for the antiderivative. So my curve is the number 3. So what I'm going to do is I'm going to graph just 3. So y equals 3. So I put a little line right here at y equals 3, like that. Of course, arrows on the side because the actual curve goes on forever. I'm going to locate the x value -2 right here, the x value 5 right here. And what we want to do is we want to find the area between the curve and the x-axis. Now, I'm not going to take too long to shade that in because it's fairly obvious what we're looking at. But what you can see is this is a pretty simple little geometric shape called a rectangle. And so, of course, the area of the figure would be 3 units tall by, looks like 7 units wide from -2 to 5. And so the area of that figure is 21. So the integral from -2 to 5 of 3 dx is simply 21. Now, again, we're starting at a very, very simple level. Now, sometimes we get a little teeny bit harder. So this one, of course, is a line. We're going to start here at 4. We're going to have a slope of 2. I went ahead and I made my axis counting by 2 so it didn't get too high. So I'm going to go ahead and go up 2 over 1 a couple of times, like this. And make myself my line. And just like the previous problem, I'm going to go ahead and find my values of x if they're wanting me the bounds of, we call these the bounds of integration. So we're going to go from x equals 0 to x equals 4 right here. And we're going to go ahead and find the area between the curve and the x-axis. And so this integral is going to be the area of this nice little trapezoid right here. So, there's always different ways to look at it. So some people will look at that as area equals 1/2 b1 plus b2 times the height. That's one good way to find the area of these. And keep in mind that in basic geometry, the bases are the parallel sides. So this little piece right here is 4 units tall, whereas this piece over here is actually 12 units tall. So those are the two bases, the parallel sides. So this would be 1/2, 4 and 12, of course, which makes 16. And the height is actually the difference between these two parallel sections, which is 4. So pretty easy little idea. 1/2 of 16 is 8 times 4 is 32. So that would be one nice representation of the area of this. Now, of course, one of the beautiful things about geometry is you can actually cut it up in a lot of different ways. I have had many, many students look at a problem like this and say, well, I don't really like trapezoids so much. I can't remember the formula. Well, if that's your story, you could actually split it in half and look at it in a slightly different way and say, you know what? I got this. I've got a little rectangle here that is looks like it's 4 units wide and 4 units tall. So we're looking at a number 16 right here. And over here, you go over 4 and up 8. And this triangle, 4 by 8 is 32. Cut that in half, we're back to 16. And so you can see that the two 16s together make a total area of 32. So give me 1 second, and I'll be right back with you guys. Okay. Hey, we're back. All right. So now, sometimes we don't have simple lines, so that's not a big deal if you don't have a line. I don't know why it doesn't want to share for me, but here we go. So this is a little form of an equation that you'd like to just memorize. This is actually the equation of a semicircle. Anytime you have something like this structure where you have a squared minus x squared, boom, that means it's a semicircle whose radius is 6. So look at the brilliant semicircle that I just made right there. It looks more like an egg than anything else, but I'm looking at this thing. And I want to find the area of that, but I know that the area of a circle is pi r squared, but of course this is a semicircle, so we're going to cut that in half. So it is pi r squared cut in half, and of course 36 pi over 2 would be 18 pi, and we're done with that problem. Pretty simple little idea. So again, part of it is just recognizing that this thing right here is a line. So if you actually put something underneath it, simple little trapezoid, this one is a semicircle, so boom, using the area formula. Now, this last one that I have in my structure is a little bit harder. You're going to notice that I have exactly the same equation that I had here, brought down to here, but from our days in pre-calculus, that +3 is simply just going to move the curve up 3 units. So it used to hit at the top of 6, and now it's going to hit at 9. It used to be at -6, it was 0, now it's going to be at 3. It used to be 6, 0, now it's going to be 3. So we're looking at this shape right here. Well, this is what you would call a composite shape, because I'm not simply asking you to find the area of the semicircle up here, but that's actually not so bad because we already know what that part is. We actually want to find the area between the curve and the x-axis. So if I actually brought it all the way down to the x-axis, I also need to find this part because the curve really is all of this stuff. And so keep in mind this base is 12 units long by 3 units high. So its area is 36. And there we go. Our total area of this particular curve, our integral would be 18 pi plus 36. So, of course, that's fantastic. That works really, really well. But, of course, we don't always get so lucky and have curves that are well-defined like that. So the last little thing that I was going to mention to you, and I've got class coming in about 4 minutes, is sometimes we have something that's a little bit harder. So I'm going to kind of try to make a simple curve like y equals x squared plus 2. Now, if you had x squared plus 2 over 1 up 1, 1, 1, 2, 3, something like this. Here is a nice little parabola. Wish I had a little bit more time to make that look pretty. But if I wanted to find the integral of x squared plus 2 dx, say from 0 to 2 right in here, and I wanted to find the area of this, that becomes a lot more problematic for us because when we look at it, we don't have basic geometry shapes to lean on, do we? It's not a nice, perfect little curve. So we have a couple of ways that we can actually visualize that. And one of those ways is to actually stuff it up with little pieces that we do know. So you notice that we have all these little squares in here, and you have portions of squares there. And so we can kind of estimate by like doing a little bit of that, but that doesn't feel very precise, especially if you don't have graph paper. But so what we'll often do is something like this. We will often take little teeny rectangles, which are actually known as partitions. And you'll notice that as I make all of those rectangles, if I could find the area of these 4 little rectangles, that actually provides a decent estimate for the area between the curve and the x-axis. But you'll notice we're missing these little pieces right here. So it's an underestimate of the curve. And so we could make it a little bit different if instead of maybe making these little rectangles hit at the left side. And by the way, when it hits at the left side, it's called left side Riemann sum. Sometimes we're going to have those little things hit at the right side. And sometimes we'll have those little rectangles. If the curve is coming up here like this, sometimes what we'll do if we want the rectangle to be in here like this, sometimes we'll make it hit right in the middle. And so you'll notice, in a sense, it's a little bit of we missed a little bit, got too much here, but not quite enough there. And that's a midpoint Riemann sum. And so we can actually estimate curves that we don't know by using shapes that we do know. And so that's actually pretty convenient. And we have some tricks that we'll address in later videos to make that estimate as good as we can to the point of it being perfect. So hopefully this was helpful. I'll see you guys back in class. Bye-bye.